We have covered energy balance a couple times. Now we're going to cover entropy balance. This is going to be for closed systems still. Now our equation we're going to have is the entropy at state 2, note this is a capital S, minus the entropy at state 1 is going to equal the integral from state 1 to 2 of delta Q over T plus this little sigma. This is the entropy balance equation. All right, so we had energy balance. This is entropy balance. Now let's write out in words what all these terms are. So for the left side, that's going to be the change in the amount of entropy that's contained in the system during a certain interval of time. Okay, so that's what the left side is. And let's put it in brackets so it's obvious what term is which. So that's for that one. Now that's going to be equal to this first term. This is going to be the net amount of entropy that's transferred in across the system boundary during that same time interval. All right, so we're dealing with the same interval of time here. So this is this. Okay, and we've seen this equation before. Now we've got this little sigma part. So plus this last term here, this is going to be the amount of entropy produced within the system during the time interval. So that's what that sigma term is for. Now, if we want to write this in the differential form, let's write out what that would be. The differential form would be ds, where that's capital S, equals delta Q over T plus delta sigma. All right, that's the differential form, in case you need it. Now let's talk about this term right here, the first term on the right-hand side. Let's look at that one and write a couple things down about it. That term is for the entropy transfer that accompanies heat transfer. And we talked about that before in one of the earlier videos. So it's just our entropy transfer accompanying heat transfer. Now there's going to be a sign convention with that, just like everything else. If you get a positive, you're going to have entropy transferred into the system. And then if it's negative, that means it's transferred out. So we'll put entropy transferred out of the system. All right, so this is going to be one of those sign conventions you might want to pay attention to. Now this sigma over here, we've already talked about sigma. Remember, we mentioned that before in chapter 5. So let's talk about sigma. So entropy is going to be produced when there are irreversibilities. So let's put entropy produced by irreversibilities. So we're going to take what we learned earlier and we're going to include it here. Now remember, if sigma was greater than 0, that means we have internal irreversibilities present. And if sigma is equal to 0, there are no irreversibility is present. And then finally, if it's less than 0, that means you've just got an impossible scenario. We don't need 3 S's here. Impossible. Right? Impossible scenario can't happen. Now, what we're going to look here at is the fact that entropy production is going to be useful then for telling us where irreversibilities occur in our system. Alright, so let's write that down. So it's useful for figuring, let me move this up so I can see it. Useful for figuring out where irreversibilities occur. Okay, and again, that's because we have this information here. Okay, so that's the end of that section. Let's look at our entropy rate balance equation, and then we'll put it all together when we get to the examples. So entropy rate balance, that's going to indicate we're going to have differentials here. We're going to have ds dt. That's going to be the summation of q dot over t. And we're going to have plus sigma dot. So this is our equation. There's a dot here, and these are just summed over some variable j. All right. Now, this right here is going to be the time rate of entropy transfer through our boundary with a temperature T. All right, so we got that, and then this term over here, that's the time rate of entropy production due to irreversibilities. I swear that word is the longest word. Okay, so that's going to be our entropy rate balance equation. We're going to stop there, and then we'll go over how to actually use this stuff in the next example. So I'll see you in the next video.